Next, we'll look at the LabVIEW VIs for controlling the signal path. So this is where we select the input and output connectors and configure the connectors. So first, in the VI tree, there's an area for the signal path configuration VIs, and you can see first row there is for connector type, and then we have VIs for controlling the various input-outputs. So we have analog balanced, analog unbalanced, analog, ASIO, Bluetooth, digital balanced, and so on. There are more in the VI tree. And the VIs here correspond to the signal path settings in the APx500 UI. So here on the left, for example, we have a VI named APx500 sequence signal path get set output analog unbalanced. And you'll notice that the controls here correspond to the controls in the output configuration area of the analyzer. So just like in the case of the generator and analyzer controls, there are more controls in these type def cluster controls than there are on the screen at any one time. That's because we have to accommodate all of the different use cases. But you can see, for example, the number of channels control here, the EQ table that corresponds to this EQ in the output configuration, and so on. We're looking at the context help view for this VI. So it runs similar to the VIs for setting the generator and the analyzer. There's a set Boolean input to this function, and it's false by default, which means it gets the configuration. And if you want to set the configuration, you would set it to true. So we pass the APx500 reference in. We have an input that's a string representing the name of the signal path. And then there's a cluster of these controls on the input side and the output side so that we can get them, reset the ones that we want, and set them using the same VI. Similarly, for the input configuration, there's a VI that corresponds to the area where the input configuration is set in the APx UI, and it's the same model as used for the output configuration. So there's a get set VI, which has, again, a Boolean set input that is false by default, which means we would get the parameters. We unbundle or bundle by name and change the ones that we want, and then we would set them with the bool set to true. Then for the filters area of signal path setup, there is a VI named signal path get set filters analog, and another one named get set filters digital. And this can be used to get and set the properties of the high pass, low pass, bandwidth, weighting, and EQ. And it has the same get set paradigm as the other VIs in the collection. There is also a VI for getting and setting the device under test delay, and there's just one simple entry here, that's the delay. So you can either get the current value of the control or set it by, again, using the set input to the function equal to true. Let's look at some of the other VIs in the driver collection. So this palette and tree show the action status VIs, and we have a number of different VIs in here. Some are specific to Bluetooth, so they're in the Bluetooth subpalette. Some are specific to the sequence mode, so they're in that subpalette. And similarly, another subpalette for PDM, which has some action status VIs specific to PDM. There is a polymorphic VI called AutoSet GenLevel, which can be used to run the AutoSet GenLevel function both in sequence mode and in bench mode. There's a run measurement VI, which is also polymorphic, so there's a version for sequence mode and one for bench mode as well. There is a VI to change the operating mode, which is also polymorphic. We'll see more on that later. There's the VI that we mentioned before to run the FFT measurement and get all points. Similarly, run the signal analyzer measurement and get the scope result, all points. You would use that if you wanted to get a raw waveform with all its points. A similar VI to run the continuous sweep measurement and get all points. These suspend and resume VIs are for sequence mode, and they're for specialized applications when you're doing very big project files and you want to prevent APx from processing the state base of the system every time. So I won't go into those. Finally, on this panel we have a bench mode VI for turning the generator on and off. Next we have the data palette and data entry or data area in the VI tree. And this has functions for getting meter results for sequence mode and also for bench mode. There's two versions for bench mode. One just gets unsettled meters and the other gets settled meters. We have one for getting results that is polymorphic, so we can get results for both sequence mode and bench mode. And then one VI for exporting meter results from bench mode. There's a VI to determine if a result exists in a certain measurement in sequence mode. Another VI for getting XY plots from sequence mode. One for getting text result. This would be for specific results like teal small parameters that return a table of results. There's a VI for getting pass-fail results, and finally one for importing limits to sequence mode. This is a screenshot of what the get measurement results VI looks like. So it's got the signal path and measurement clusters in and out, and then there's this large cluster called measurement data set. And this basically for any measurement contains the all of the results that can be returned. So there's an array of clusters for XY results. This would be results like level versus frequency. There's also one for XYY results, and this would be for a result that has both a left data axis and a right data axis. So for example, if you were plotting RMS level on the left axis of a graph and THD plus N ratio on the right axis, you would use this cluster to return that data. There's one for getting meter results, which would be the simple single value results like level or gain. One for the raw text results, and then a specific one for the teal small results. This VI is for getting bench mode results. So it's similar to the previous one, which was specific to sequence mode. And in bench mode, there is an array of clusters representing the XY results of a measurement, and similarly an array of clusters returning the meter results. So you can see values in here like the meter result name, the meter unit, the readings, and there will be an array that matches the number of elements in the array corresponds to the number of channels that are being acquired, and then some Boolean indicators that show whether the upper or lower limits were passed. This is the utility palette and the utility section in the VI tree, and there's just a large variety of VIs here that can be very useful. One that I use very often is right here. I'll try to highlight that with the laser pointer. It converts a set of strings to the signal path and measurement object. Then we have VIs to get or set which measurement is active, a VI to add a signal path or add a measurement, to get the checked state of a measurement, to set the check state, to find a measurement, to find a wave file name. Here's one to load a wave file, one to open a project file. So really just a lot of very useful VIs in this utility collection. One that we talked about already is the APx error handler. It's found here on the utility palette. Then we have the bench mode palette, which has a number of functions specific to bench mode. So we can access the acoustic response in bench mode, similarly the continuous sweep, the FFT measurement, the recorder measurement, the sweep measurement. Here's one for nested sweeps, which is polymorphic, so it can be used to control nested sweeps both in bench mode and sequence mode. Then we have one to control the generator in bench mode, to control the analyzer in bench mode, to get or set the state of the analog filters, another one for the digital filters, and then the device under test delay. There are also some examples that ship with the driver collection, and I'll just run through those briefly here. So there's an examples palette that is part of the LabVIEW driver. The examples are also shown in the tree. And there are a number of very simple VIs that are well documented to show how things work. I'll just show some of these in this screenshot. So the one on the left here is called reference levels auto set gen level, so it can be used to automatically set the generator level to a target value. The one in the middle here can set or read the state of the aux control input-output ports on the back of the analyzer. This is a general purpose digital I/O port with 8 bits in and 8 bits out that can be used to say set relays or read the value of a switch, for example. Then we have one to configure the digital unbalanced output connector. The one in the lower right panel of the screen here is to set the output connector type. So just some very simple examples. One thing that I wanted to emphasize here is the importance of using a LabVIEW project and a configuration file. Now the reason for doing this is that when using .NET with LabVIEW, it can actually cache references to older versions of an assembly. And this is very problematic. We found this out the hard way with our LabVIEW driver. So what would happen is you would create a LabVIEW program for, say, APx 4.2. You, at some point, upgrade to 4.3. You open your LabVIEW VI, and everything is broken. And it's really difficult to figure out what's going on. And it turns out that LabVIEW, inside the LabVIEW VIs, will cache references to an earlier version of the APx API assembly, and this can happen even if the previous version of APx has been removed from the computer. So it's very, very difficult to work with, and this is a way to get around it. So what I've highlighted here, the name of this project is APx500 Examples project.lvproj. And you'll notice highlighted in this red rectangle, there's a file named APx500 Examples project.lvproj.config. So it's got the same name as the LabVIEW project right down to the .lvproj extension, and then it has an additional extension .config. And if you open that file, it's an XML file. I've opened it with Notepad here, so it's just a text file that can be opened with a text editor. And there's really only one statement here you need to worry about, and that's circled or highlighted with this red rectangle. And I'll read that out. It says binding redirect old version equals 2.1.0.0 dash 4.3.0.0, new version equals 4.4.0.0. So what that does, it's reflected in the name binding redirect. It's basically telling LabVIEW that for any references to the old versions between 2.1 and 4.3, don't use those, but instead use version 4.4. And you can also change these numbers around to force LabVIEW to use a specific version of the API. So for example, let's say you've been working in 4.4 and you want to go back to 4.0 for some reason. You can force LabVIEW to use version 4.0 of the API by just changing these numbers appropriately. So I would encourage you to use a LabVIEW project for your VIs, keep all your VIs in the project, and use one of these config files. And you can simply copy this one and rename it to match the name of your LabVIEW project. That file should reside in the same folder as your LabVIEW project. Then when you open your VIs from the LabVIEW project, it will automatically choose the correct version of our API. So this is very important. And This example project is located in the instrument.lib folder of LabVIEW under Audio Precision APx.net. We'll look at some tips for constructing LabVIEW projects here. So first of all, initializing the driver and switching modes. So with this polymorphic VI, you can start in sequence mode. There's also a version of it that allows you to start in bench mode. You can start in bench mode and then call this mode switch VI to, you could start in sequence mode, call the operating mode VI to switch to bench mode. Similarly, you could start in bench mode and call the operating mode VI to switch to sequence mode. This shows how the APx object or reference is passed around through the VIs. So typically you would call the open VI, which gets the reference to APx500, and that's passed through all of the VIs downstream. Similarly, you would wire the error cluster to all the VIs to make sure that error handling is passed all the way through the chain, and you can handle any errors that occur. One exception to this is the nested sweep object here. So it has a reference to one of the properties for the nested sweep that is a subset, or it's not the main APx500 reference, and that's shown here. Similarly, if you call the measurement VIs, they will pass this data cluster to VIs that get the XY plots or the meters. And these do not have the APx500 reference to them because they don't have any, they don't really use any of the API functions, so they don't need a reference to the APx500 object. You can also call this close VI when necessary, and we typically don't call it because the way it's configured is it actually closes the APx500 software completely. And for those of you who've used APX before, you've probably noticed that the first time you load the software, it takes quite a while to load. It can be up to 40 seconds, I think. It can be longer if you're doing a version change because it uploads firmware. So you don't want to close it every time your VI ends. Instead, you could just use close a .NET reference and not close the APX500 software. Now, I'd like to cover constructing LabVIEW VIs, and when you want to get at some of the properties and methods that have not been exposed in our LabVIEW driver VIs. So we'll talk about that in this next section. So if you put the open VI for APX500 on your block diagram, you can right-click on the output of the APX500 reference. And one of the menu choices is create property for the APX500 class or method. And if you select property, for example, you'll get this huge list of properties that corresponds to all of the top-level properties that are available in the API. So for example, you've got entries representing all of the measurements in sequence mode and so on. So if we wanted to work with the level and gain measurement, we could select level and gain here, and that would drop a property node called level and gain. Next, we would right-click on the output from that level and gain reference, select create property for that level and gain measurement class, and we could choose one of the properties we want to work with. So if we wanted to control the generator, we would choose property generator. Next, we would right-click and select create property, and we would choose one for analog level. So really, we're showing you how to build out working with the level and gain measurement, setting the generator's analog levels. And as you continue down the chain, you can see here that we're going to get level and gain, generator, analog levels. We have a method now called setValue, which has inputs channel and level. So we're setting channel 1 to a level of 0.75 and channel 2 to a level of 0.5. Now, these properties, when you plunk them down on the block diagram, they are a get property by default. In other words, well, in LabVIEW this is called read. And you can right-click on these and select Change All to Write or Change to Write. So for example, here if I wanted, instead of reading the state of the analog sign generator, I wanted to turn it on, I would select Change to Write, and then I could wire this Boolean into the property, and that will cause the generator to be turned on. If you certain properties, if you create a property off a reference, in this HDMI output, for example, it will create an HDMI output settings property, and you can see an input to that is this property called video format. If you right-click on that and select Create Control, it'll create an enum control that has the enums that are available to work with the system. So that's a good way to create enums to work with the properties that require enums or return enums. An enum is short for enumerated type. So finally, I think that comes to the end of the presentation, and I think what I'd like to do in parting is show you this LabVIEW example. So this is an example that we've created that matches similar examples created in other programming languages. So we've been giving a seminar on using the API with APx500, and we covered a few different programming languages like C# and Visual Basic.NET, and they all have a common example that we've recreated here in LabVIEW. So we'll go through this. It's a good illustration of using some of the built-in VIs from the .NET LabVIEW driver, and also from getting at properties and methods that are not exposed by the drivers in the driver collection. So let's go ahead and load that example, and I will walk you through it. So here is here's the front panel of the VI. So it has 3 buttons on it: Load APx Software, Sequence Automation, and Bench Mode Automation. So let's look at the block diagram, and we'll see how this all works. So this is in LabVIEW it's called the design pattern, and this pattern is called a producer-consumer loop. So it's a set of parallel loops, and the loop on the top basically controls the loop on the bottom. So we have a queue running here, and this structure in the top loop is called an event structure, and it only any case in the event structure is executed only when the event that it is servicing gets fired. So for example, this first case services the Load APX button here. So this is the button on the front panel. If I press Load APX, it'll jump into this case and enqueue a state called Load APX. And there are a number of different states in this enum control. When that happens, it'll go down to the lower loop, dequeue that element, and it will run this case called Load APX, which has the APx500 OpenVI. The next event case services the Sequence Automation button. So when that button is pressed, it will enqueue this state called Sequence Auto that will get dequeued down here in the consumer loop, and it'll go to the Sequence Auto case. And in that case, we switch to sequence mode. We load a sample project from the directory one level above where this VI is. We then run the sequence, and then we display the results. So let's first look at that. Let's just run those first two buttons on this case. So first we'll run the VI. Then I'll click the Load APX Software, and all that does is get a reference to the APX software because it's already running. And next let's do the Sequence Automation. So I click Sequence Automation. It'll load a project file, and it's going to go ahead and run the sequence. doing a stepped sweep here, and then it just gives me back the data. So I created this little VI that just displays the data. So I have the RMS level, the gain for 2 channels, and the peak level from the level and gain measurement, and then the step frequency sweep result, which is just RMS level versus frequency. And this shows the deviation result, and the units of the deviation are in dB. It's a pretty simple example. Next, let's look at the block diagram, and we'll cover the bench mode button. So the button on the front panel is bench mode automation. That's this button here. And you'll notice this one looks a lot more complicated. We have a lot of states in here. So I'll go through these. They're basically grouped into 3 groups. The first group here configures bench mode input-output, then configures the bench mode filters. We then configure the bench mode generator and analyzer settings. We add some meter results to bench mode. We configure settling, and we get the meters. So let's look at the cases for those now. So the first one is bench configure IO. So this one selects bench mode as the operating mode. We then set the analog balanced as the the output connector. With this VI, we get the properties of the analog balance connector. We bundle by name the ones we want to change. We set the number of channels to 2 and the source impedance to 100 ohms. We then set those properties. Next, we select and configure the analog balanced input connector. Again, we select the connector, we get the current properties, bundle by name, and change the value of the ones that we want to change, and then call that VI again with the set Boolean property set to true. The next case is the bench configure filters. So here we get the input filter settings. The same procedure, we bundle by name and change the values of the ones that we want. So we're changing the high pass filter to DC, the low pass filter to elliptic with a 20 kilohertz corner frequency, and then the bandwidth we're setting to 90 kilohertz, and the weighting filter to none. Next, we set the device delay to 0 seconds. This one here is an example of using the primitive .NET nodes to do something. So we've set the input to loopback in this case. So I've taken the reference to APx500, gotten a property for bench mode, from that a property for setup, and from that a method called loopback, and I've wired a Boolean true to that. So that's the same as checking the loopbacks checkbox in the software. Next, we have the bench configure generator and analyzer. So we have VIs to get the generator settings. We bundle by name and change the values that we want and set those. Similarly, on the analyzer settings, we get the current values, bundle by name, change the ones that we want, and then set them. The next case is, now this one, there weren't any VIs in the driver collection to do what's being done in this example. So we have to use the primitive .NET nodes. So this deletes all of the bench mode meters and adds back the desired meters. So we have the bench mode meters. We show the meters. This gets the number of meters in bench mode. We go through a loop and remove the meters one at a time in reverse. And you have to do it in reverse because then count changes. So anyhow, that's why it's done in reverse. Next, we get a meter type. So we choose to add back a bandpass level meter, a DC level meter, a gain meter, and a THD plus N ratio meter. And these VIs just add those meters in, and then we enable those meters. The next case is to configure settling, and again, there were no built-in VIs for this, so here we're getting a reference to bench mode, analyzer, settling. We're setting enabled equals true, the reading timeout 5 seconds, I think it is. Track first channel is set to true. We then get the RMS level meter and reset it to default. We get the bandpass level meter, and then we get channel 1, and here we have the settling parameters, so we set the algorithm to none, the delay cycles to 4, and so on. So we're configuring all the settling parameters, and then at the end here there's a reset to defaults, which was done in the other examples. Next, there's a case called bench get meters. So this will get the values of the meters, and we're calling this driver VI, which will get the settled meter values. First, we have to build up this array of clusters representing the meter and its units. And there's one per bandpass level, DC level, gain, and THD plus N ratio. Then I've connected them to this little function which will just display the meter results. So that covers the first group up here, working with the meters. The next group runs the sweep measurement in bench mode. So there's a case called hide bench or bench hide panels, bench configure sweep, and bench run sweep. So let's look through those cases. So the bench hide panels, this hides the signal path setup and generator analyzer panels. We add the THD plus N versus frequency result as the right axis result to the first graph in the sweep measurement. So the left axis is going to be RMS level, and we're adding THD plus N ratio as the right axis. And again, there were no VIs in the driver collection to do that, so this shows how it's done with the .NET property nodes and invoke nodes. The next state is to configure the sweep. So there's a VI to get the sweep properties in bench mode. It's the get set VI with set to false. We bundle by name and change the parameters that we want to change. We then call the same VI with the set equals true. And then this VI will configure the nested sweep parameters. So for the sake of expediency in this example, I've set the nesting to none because it would just take more time to run a nested measurement. But this shows how you can set the nesting parameters. So essentially, like the other VIs, you get the properties, bundle by name, change the properties that you want, and then set them again. The next case is to run the bench sweep. So this is a VI to run the sweep. We run a bench mode measurement, and it's got an enum input called named sweep. So that runs the sweep measurement. And then I've created a little custom VI that will display the bench sweep results. And then finally, we have the FFT group over here in the top case, the event case. So we have bench configure FFT and bench run FFT. And those states are represented here in the case selector. So we have bench config FFT. So first we make the bench mode FFT the active measurement. And that's done with the .NET property nodes and invoke nodes. And then we get the bench mode FFT measurement settings. We bundle by name and change the ones that we want, and then call that same VI with the set boolean equal true. Finally, we run the FFT measurement. So I'm using the same VI that I'm using for the sweep, but I have a different enum input, which equals FFT. And finally, I display the FFT results with a little custom VI. So let's move that block diagram out of the way and run this example. So we'll just click on the bench mode automation. So first thing it does is flip over to bench mode, of course. It removes the meters and then adds some of them back. Does a measurement with settled readings, and I have this little panel displaying the results. So you can see I've got bandpass level on channel 1 and channel 2, pretty close to 1 volt, matching these values in these indicators, and then meters to match the gain and DC level. Those are off the screen right now, but I can expand the display here to show them. So we'll click OK, and then carry on. So the next thing we're going to do is run the sweep measurement. I've created a sweep with a small number of points here, just 5 points, and you can see where we have RMS level on the left axis, THD plus N ratio on the right axis, and you can see that the results collected with LabVIEW match what's on the screen there in APx. So that's an example of how to get the data back for a sweep. And next it'll do the FFT measurement and then display the FFT. So the VIs were used to set a bunch of these parameters here. We've set the acquisition length to auto, the FFT length to 16K, and so on, chosen the window. And here you can see the FFT result brought back to LabVIEW, and then the scope result is in the background here as well. So that's basically it. So you're welcome to have a look at that example. It'll be available in the download area, and you can walk through that and see how that whole thing works. Just going to stop this and close it for now. And then we'll carry on back with the presentation here. So we've gone through that example. So that's really the end of the presentation here. And in conclusion, I just wanted to leave you with a couple of points. So the APx.NET LabVIEW driver provides many VIs that really simplify basic control of APx analyzers with LabVIEW. It doesn't provide access to everything, but you can access everything, the entire API, by using the .NET property nodes and invoke nodes. So you can definitely do what you need to do. And a couple of key points that I'd like to emphasize. Be sure to use a LabVIEW project file with that accompanying .config file. And also, I would encourage you to use the APx Simple Error Handler VI, because if you don't, you can get some very cryptic error messages that are quite difficult to work with. And that is the end of the presentation.